Yeah, before the press release, go back to the subject of the mitigation. So this is a work I'm doing with colleagues from a small company, Odysseus Space, that has its headquarters now in Luxembourg, and colleagues from Paris Observatory, the CCUS Space Center and Campus in Paris. So here we will present some concept of SmallSat to do reconnaissance or exploration of hazardous asteroid and advocate the use of SmallSat and CubeSats. So far, we have a few missions that already visited some small bodies. Small bodies means asteroids, comets, and irregular satellites as well. So we have the list of the asteroids here on the top, and then the comets and a few satellites like Phobos, Deimos, and moons of Saturn. But I wanted also to point out from this table that most of these visits are simple flyby, where you have mostly a snapshot image of the body and sometimes the mass. And our aim in developing this BIRDY CubeSat is to get more information on the mass or internal structure of these bodies in general, and probe the interior. But of course, as we have already said in the previous session, starting at the beginning of the week, knowing the mass of the body is important if it's a hazardous asteroid, and knowing also its interior when it's a rubble pile, gravitational aggregate, is also important. And to have this important for the risk assessment, to know what will be the vulnerability if it impacts the Earth, and also important for the mitigation action itself. So our aim is to probe the interior and start first with the basic knowledge of the mass, the center of mass, then go to density, porosity, and more, or coefficient of the mass distribution inside of the body, if it's possible. And for that, we are working on a space mission using SmallSat or nanosats or CubeSats, depending on the weight of the satellite and also the standardization we are using. So CubeSat has some advantages and has been developed for the last decade already. Compared to traditional mission, it has a reduction of the cost for launch system, because it is launched with over satellites in general. It has also a reduction of the cost for the development, because it makes use generally of components on the shelf, the so-called COTS components. And now we have more and more opportunities of CubeSat that have been developed, constructed, and deployed, and more and more launch opportunities also in general. Of course, these are mostly for the moment CubeSats in orbit around the Earth and low Earth orbits. Developed basically, I forgot, I should add here, for commercial use, but then also the beginning was educational purposes, also with some now going for technological demonstration, and we start now to have more and more CubeSat also for the performing science. In our case, the advantages is also to have a small satellite that can perform its own task, dedicated task, or small missions. It's also a small satellite that is fast and to develop, and small time for getting the readiness, which is also quite important when we are talking about reconnaissance mission, as we have seen already. And it is also of some interest because we can take more risk with these small satellites that have lower cost, more risk than would the motorcraft do. Yeah, so for these, some advantages to go for nanosatellites or CubeSats. And we have here some example of, some people that is the structure to deploy the CubeSats that are standardized. And we have also an example of CubeSat that have been already flown, 6 CubeSat here from Planetary Resources, and here from the JPL, the Marco CubeSat, which is the first interplanetary CubeSat. For the moment, most of the CubeSat are around the Earth, and going to deep space put some challenges because for reason of radiation, reason of thermal control, of energy supply, etc. But there are ways now to go there, and Marco have shown us the way. So our BIRDY concept is to have a CubeSat piggybacked with a mothercraft, and then yes, to go to a small body, and here in particular to go to a precursor mission before the mitigation of a hazardous asteroid has been advocated already with this exercise of 2019 PDC, advocated also within the annual SHIELD 2 program, research program. So we go with a mothercraft. The mothercraft acts as the carrier to bring us there, and also as a communication relay with the Earth. So we don't need to have the big antenna on the CubeSat itself, and so we can get closer to the asteroid, take more risk, and do proximity operations. I will go through the payload later on again, but the basic idea is to perform radio science in addition to imaging, and we can also add some other additional instrument without putting too much on the small CubeSat, like high frequency or low frequency radar. And the target size is 3U to 6U, which are units typical in the CubeSat, and 6U might be the typical size for interplanetary CubeSats. So again, we are studying different parts of this kind of CubeSat. So we want to have a propulsion for the attitude and the orbit control. We want to have imaging capabilities and also auto navigation to increase the autonomy of the CubeSat itself. And then to have a radio science with radio frequency communication for doing precise orbit determination. For the autonomy in the navigation, we are developing the concept of object tracker. That is not only a star tracker looking at the position of the stars, but also at the position of, I don't know if we see very well, and the pointer doesn't work neither. So we have background stars here, and in the foreground solar system objects. So this is a real image with the Earth, the Moon, and Mars, and having the motion, observing this parallax with the foreground object in front of the background object, we can get the position of the satellite in space. So from asynchronous triangulation, we can get the position, and we are working on that to increase the precision of the position, starting with precision of the pointing of the observation of 0.2 arcsecond. And now for the planetary defense, we have two cases basically. Depending on the warning time. The best case is to have a rendezvous, as Brent BIRDY already showed before. And the worst case is when we have no time to have a rendezvous and a single flyby, the quick reconnaissance. So in the rendezvous case, then we can have a deep knowledge and do the mass determination and the porosity determination, in addition to have improved orbit of the body. And if we can stay longer, we can also have the post-mitigation validation, measuring the orbit before and after the mitigation. In the worst case, when you have only a single flyby, it's harder to have mass determination, if not harder, just impossible. But we can still have imaging of the body, of the shape. Is there a satellite, knowledge of the surface of the body with the borders, etc. And we also can imagine to have not only one CubeSat, but replicate CubeSat. Eventually, one of the CubeSat could also hit the surface of the asteroid and show how the surface reacts. And again, we can have a refinement of the orbit before the mitigation itself. So for the mass determination, in case of rendezvous, we are looking at this kind of inter-satellite link with measurement of the radial velocity of the nanosat and the main spacecraft. And also another option is also to have direct link with a VLBI observation of the CubeSat. I will summarize here just to see that we can have a different application for doing science, for doing exploration of planetary resources, but it can be very interesting to have this kind of concept of CubeSat doing the reconnaissance and can cope the worst case where we can only have a single flyby to the best case where we have more time and doing our audio. So I'm finishing here. I'm ready for the questions. Thank you.
Questions? Otherwise, thanks so much. And this concludes session 5.
Okay. Thank you.